Hello everyone, here are the solutions to logs day 11 and 12 to begin with. I'm going to scroll through slowly. Now for day 12, part C, as soon as we were to take the natural log of both sides, we can't take the natural log of a negative number, so it's just not possible. Or if you think of the graph of e to any exponent, it's never going to get past 0. We have a horizontal asymptote at 0 here, so that's never going to intersect the line y equals 1. So a couple ways to determine that. All right, so I just wanted to address on pages 87 and 88, I believe it was, where you had to find the average rate of change over an interval. When we're using an interval, or given an interval, it's just easier to use this formula for it rather than looking at it as x plus h and then x. But if we're just looking for the average rate of change generally, or at just one certain x value, then we can use the difference quotient here of f of x plus h minus f of x over h. So please let me know what questions you have over these pages. I'll probably, to the assignment I'm going to give today and to this one, I will make a solutions video for you guys to see. But I do want to address number 13 here. So here we were asked for the slope of the tangent line for this function here, f of x is equal to the absolute value of x. So a couple ways we could do this. We could say slope of the tangent line, which is the limit as h approaches 0 of f of x plus h minus f of x all over h. Well, if you picture the graph of the absolute value function, which is going to be the second way I'm going to show you how we can look at this, I want to take this from two different sides of 0. So if we were to look at h approaching 0 from the left of the absolute value of x plus h minus the absolute value of x all over h, we need to remove these absolute value bars. So when we're to the left of 0, we're looking at negative numbers. And if you take the absolute value of a negative number, it actually turns into its opposite. So now this is behaving as the opposite of these expressions. So as h is approaching 0 from the left, this absolute value of x plus h is actually behaving like the opposite of x plus h, and then minus the opposite of x all over h. So if we were to expand this, we're going to get a negative x minus h plus x all over h. The x's are going to cancel out, and then we're left really with a negative h over h, which is going to give us a negative 1. So now if I took a look at the limit as h approaches 0 from the right of the absolute value of x plus h minus absolute value of x all over h, when we're looking at a positive number, the absolute value of a positive number maintains its same sign. So now this will just become, again, we need a limit here, just x plus h minus x all over h. So here the x's are going to cancel out. Now h divided by h is just going to turn into a 1. So that's the slope of our tangent line. Or if we think about the graph, if we actually go ahead and graph it, we could look at this as a piecewise function and really look at two separate lines right here. So the slope of any tangent line, when we're tangent to a line, it's still a line, and it has to have the same slope. So every tangent line we draw in over here, slope of all of our tangent lines are going to be a positive 1. If we look over here and draw in a series of tangent lines, all of their slopes are going to equal a negative 1. So when we're over here for all x's greater than 0, the slope of the tangent line is going to equal 1. For all x's less than 0, the slope of the tangent line is going to equal negative 1. I'm not going to address this right now, but we will get to it. What is the slope of the tangent line at x equals 0? That's another lesson for another day. So if I'm looking at x equals 2, that puts me over here because 2 is greater than 0, so the slope of the tangent line is going to equal a positive 1. When x is equal to a negative 3, that puts us on this side of 0, so the slope of our tangent line is equal to a negative 1. All right, so I just want to review because there's a very good chance I can ask you a question about these on the test, just to go over explanations for the different flavors of discontinuity. So we want to be very clear, sketching a graph and indicating everything about this type of discontinuity. So when we have a removable discontinuity, we could draw something like this, or typically we've seen just a line with a hole in it. But what you want to do is indicate a certain x value and a certain y value because we want to eventually say we can remove this discontinuity. So this is a good example to explain this type. So we would point out first where it's discontinuous and that it can be removed. So if you phrase it like this, you're going to be in good shape. This discontinuity can be removed if we assign f of 5 is equal to 3. Right now, this is discontinuous at x equals 5, or f of 5 does not exist. So this discontinuity can be removed if we assign f of 5 is equal to 3. Now f of 5 does not exist. So also right now we would say discontinuous at x equals 5 for right now. But we can remove that if we assign f of 5 is equal to 3. Next, we have a jump discontinuity. What causes this type of discontinuity? It's when the limits are not equal. So notice again, I put a special x value here, so I want to talk about that. So we would say this discontinuity is formed because the left-hand limit does not equal the right-hand limit, specifically at x equals 1, or I could say x equals 2, or x equals 3. An infinite discontinuity, you could draw in the asymptote. It's not necessary, just as long as you're indicating where we have a vertical asymptote. But an infinite discontinuity, an example is the graph of y equals 1 over x. This discontinuity is at x equals 0, since the left-hand limit keeps decreasing without bound, and then the right-hand limit is increasing without bound. So again, the limits aren't equal, but it's not a jump. It's an infinite discontinuity. But again, I pointed out at x equals 0. And then the fourth type, an oscillating discontinuity, we saw that the best example for this is y equals sine of 1 over x. Make a little sketch here. And again, we could point out at 0. Again, we could put a 0 in for that third explanation. This discontinuity is at x equals 0 since f of 0 does not exist. Also, the function is oscillating way too much to determine a limit as x is approaching 0. So make sure you study those four examples, the sketches, the explanations. We want to be as clear as possible. If I ask you to explain this on a test, especially on the AP exam, you want to be able to explain this as well. All right, so here are some more review problems. I will already have the solutions posted, whether it's just handwritten or as a video. So looking at these, again, just going back over 2-4 and then the chapter 2 review. Also in the book where it says the slope of a curve, it just means that's the slope of the tangent line.